Hello, Rouse. For lesson 2.2, in the video portion, I want to take a look at the proofs of the rules, or an attempted proof for a rule, and then we'll see where we kind of get stuck for now. Instead of writing them all out, I think I'll just go over proofs that I've generated previously. So let's look at the sum rule. If we have h of x being the sum of two functions, f of x plus g of x, let me just give you a quick little example of this. Not all students have had a chance to look at combinations of complex functions in advanced functions, but everyone has seen a function that's defined as a sum of two other functions. Even if you just consider f of x to be the function x, it just does nothing, and g of x, maybe not a great example here. Let's let f of x be a function that squares your input, and let's say that g of x is a function that adds 1 to your input. Then h of x is going to be, or here, let's just have g of x be, no, that'll work. That's fine. H of x is going to be a quadratic. There you go. It's a horizontally translated and vertically translated quadratic. Okay. I was going to say, even if you had the f machine doubles your input and the g machine is a constant function 1, then the h machine might be a line with a slope of 2 and a y-intercept of 1, or a vertically stretched by 2 and vertically translated up 1. Okay, you've all seen sums of functions before, even if you didn't finish Unit 7 in advanced functions. Okay, so if h of x can be written as a sum of two differentiable functions, two functions whose derivative exists, then I can say that the derivative of h of x is going to be the limit of, and here's my first principles definition, h of x plus delta x minus h of x all over delta x. Notice I can't really take the limit as h approaches 0 because h means something different in this example. Step 1 is to go to the specific definitions. So h of x plus delta x is going to be f of x plus delta x plus g of x plus delta x. When I subtract h of x, I need to make sure that I am subtracting the quantity f of x plus g of x. And my denominator is delta x. Okay. First thing that I do is, keeping in mind I'm taking the limit of this expression, I decide to split this up into two fractions, and I change the order around a little bit. I do I apply the distributive property of subtraction through sums, or multiplication by -1 through sums. And then I see an f of x plus delta x minus an f of x all over a delta x, plus g of x plus delta x minus g of x all over delta x. And then, maybe not a surprise, that to prove the sum rule for derivatives, I use the sum rule for limits. The limit of a sum is equal to the sum of limits. So this will be the limit as x approaches 0 of this, plus the limit as x approaches 0 of that. What does this look like? The limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That's a delta y. That's a delta x. What happens as delta x gets very, very close to 0? My average rate of change is going to converge on my instantaneous rate of change, and it will be a function that yields my instantaneous rate of change. Here is a instantaneous rate of change function for g, also known as g prime of x. So this is super useful for us because if we have, say, let's scrap paper again. If h of x is, I don't know, x squared plus 2x plus 1, then h prime of x is going to be the, let's mix up notations a little bit, the derivative of the first plus the derivative of the second plus the derivative of the third. So you can actually, you are considering it to be three separate functions. A lot of people lose track of this when they just start using their derivative rules and saying 2x plus 2. We'll have to talk about these derivative rules later because we haven't proven them yet. Okay. Let's take a look at products and see why the derivative of a product is not the product of derivatives. We will develop a product a little bit later, and we'll actually get this far and then do something with it. But if h of x is equal to the product of two functions, h prime of x is going to be, here's my first principles definition. I substitute in my specific definitions again, except now I'm going to have h of x plus delta x times g of x plus delta x minus f of x times g of x. So I can try splitting this up into two separate fractions, and it looks like here I distributed the division and then used limit of a difference rule. But notice how I'm not finding the derivative of the first times the derivative of the second. I'm going to say here I have no ideas. So it's definitely not. I don't want to ruin my masters here. If h of x equals f of x times g of x, in the general case, h prime of x does not equal f prime of x times g prime of x. I think we showed that in class, and we showed that to deal with products for right now, we might have to expand. Okay. Constant multiple rule that I made use of in my first numeric example. If f of x is a constant multiple of some other function g of x, like y equals 2 times x, it's a constant multiple of the function f of x equals x. Here is my first principles definition. Specific equation then, f of x plus delta x is going to be a constant multiple times g of x plus delta x. F of x is going to be a constant multiple times g of x. Well, notice in my numerator I have a constant multiple, so I use a common factor of c. I remove a common factor of c. And again, maybe not a surprise here that if I have a constant multiple of a function, that I'm going to use the constant multiple of a limit property. I didn't find the opportunity to use the limit of a product rule up here because I still had a difference in between them. But here's a limit of a constant multiple of an expression being a constant multiple of the limit of the expression, and this expression I recognize as g prime of x. Okay. All right, the power of x rule, I think I will try to walk you through the proof slow enough that I need to write it down. If f of x is equal to x to the exponent n. Now, this rule is true if n is an element of the real numbers, but for my proof, I'm going to be using n being an element of the natural numbers. We will be able to prove this rule for all real numbers by the end of this course. But for right now, we're going to prove it for natural numbers and then assume that it works for real numbers and confirm it by observation. So this is like the power of x rule, only on an expression of positive 1x to the exponent 1 raised to the exponent n. So f prime of x is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. Right back to first principles. We're learning these new derivative rules because it's so much faster and more efficient than first principles, but don't lose track of where you came from. You will be asked to use first principles in this course. So let's use a specific definition here. F of x plus h, let me get my limit notation here. F of x plus h is going to be x plus h to the exponent n. F of x is going to be x to the exponent n. And notice how expanding is going to be problematic because I don't really know what my exponent is. I suppose you could say if you wanted to expand, you would need to pull out Pascal's triangle and you figure out what the nth row of Pascal's triangle is. But that's problematic because Pascal's triangle is very difficult to generalize. You could try it if you've completed mathematics of data management, but it's still a headache. So instead, what I'm going to do is I'm going to factor this as a difference of n's. And I hope that we've observed that a difference of squares has a factor of x minus y in it, that a difference of cubes, I'm going to regret using this space for this a little bit later, has a factor of x minus y in it, x squared. Notice there's going to be a plus an xy plus a y squared. Even a difference of fourths. I mean, when I factor it as a difference of squares and then another difference of squares, were we convinced that there's always going to be a difference of the powers when you have a difference of n's? I hope so, because that's kind of the trust that I'm going to be asking for. Yeah, I'm going to need a lot more space here. So what I'm going to do is I'm going to factor, I can use this space to say what I'm doing. I'm going to factor this as a difference of n's. I could also use the factor theorem argument here, or the remainder theorem argument here, that if you've got x plus h to the exponent n minus x to the exponent n, notice that if x plus h is equal to x, if x plus h minus x is equal to 0, then x plus h would be equal to x. And if x plus h is equal to x, then this difference is going to be 0. And since the expression has a value of 0 for an input where x plus h is the same as x, that means that it has a remainder of 0. And if it has a remainder of 0, that means that x plus h minus x is a factor. And all we need to do is figure out what our quotient would be. And this isn't that hard to do, especially since we can figure out like the first term and the last term pretty easily, and then sort of trust that it works for the other terms. So x plus h times what would give me x plus h to the exponent n? Wouldn't it have to be a power with the same base, and wouldn't its exponent need to be 1 less? Let's try n minus 1. Okay. Let's take a look at our last term. You're going to have an x times something to give me x to the exponent n. Well, wouldn't that have to be an x to the exponent n minus 1? Now, the other terms will make a little bit more sense if we have seen an expansion through Pascal's triangle. That after your x to the exponent, let's look right here, after your x to the exponent n minus 1 term, your exponent on x went down by 1 and your exponent on y went up by 1. So I'm going to decrease the exponent on this by 1 and increase the exponent on this power by 1, giving me x plus h to the exponent n minus 2 times x to the exponent 1. And then before this term right here, before the y squared term, I had an expression with 1 more power of x and 1 less power of y. Let's have 1 less power of this, x to the exponent n minus 2. And then right here we would have an x plus h to the exponent 1. Okay, you kind of have to trust how this would work out here, that when you have x plus h times x plus h to the exponent n minus 1, you'll get x plus h to the exponent n minus 1. And then notice you'd have another factor of x, so that this term, this times this minus this times this, would actually eliminate to 0. You can see it happen if you expand here as well. You'll have plus x squared y minus x squared y. The multiplication of this added with this will add to 0. Okay. Have a look at it. Have a look at the expansion of I don't know, x. Even just doing x plus y the exponent n. Reviewing that expansion will sort of help you trust this factorization. And now let's start tidying this up. You've got an x plus h minus x. That'll eliminate and leave you with a factor of x. Unfortunately, I think I just have to write this down again. X plus h n minus 1 plus x plus h to the exponent n minus 2 times x to the exponent 1 plus dot 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 plus x plus h x to the exponent n minus 2 plus x to the exponent n minus 1 all over h. Now, this is when, as a teacher, you usually regret or have some regrets in saying that you need to show the expression in a determinate form. Because one more time, and I hope it's the last time, I'm going to have to write out this expression again. X plus h to the exponent n minus 1 times x to the exponent 0 plus x plus h to the exponent 1 less than that, n minus 2 times x to the exponent 1 more than x to the exponent 0 plus all the way up to x plus h to the exponent 1 times x to the exponent n minus 2 plus x to the exponent n minus 1. Okay. Now let's start tidying things up, because this is now out of the indeterminate form. It is now in a determinate form. And I'm going to use the limit of a sum property and the limit of a product property all together as one. As h approaches 0, this right here is going to go to x to the exponent n minus 1. As h approaches 0, x plus h approaches x. That'll be raised to the exponent n minus 2, and I'll multiply it by x to the exponent 1. Maybe in here I'll try to convince you the next term would be x to the exponent n minus 3 plus, times x squared. All the way down to as x approaches 0, that approaches x. This will stay x to the exponent n minus 2, and then that'll be x to the exponent n minus 1. Okay? So here's where the interesting thing happens. When we multiply, here we've got n minus 1 factors of x. Here we have n minus 2 factors of x, and then one more factor of x. I didn't want to say plus one more factor of x. We're multiplying by one more factor of x. So I'll keep my base and I'll add my exponents. You have n minus 2 factors. What's one more than n minus 2? N minus 1. What's two more factors of x than having n minus 3 factors of x? N minus 1. The tricky thing, I suppose, is keeping track of how many terms there were here. And that's something that I probably should have mentioned a little bit sooner back here. I think we have a couple of ways of counting this. Do you notice that when your exponent was 2, you have 2 terms here? When your exponent was 3, you're going to have 3 terms here. Now, this is because we could generalize this. When your exponent is 3, you're going to have an x to the exponent 2, an x to the exponent 1, and an x to the exponent 0 term. Here we're going to have an x plus h. Let's count the x plus h's. You have x plus h to the exponent 0, and then your second term from the right is x plus h to the exponent 1. So by the time you get to n minus 1, this is actually the nth term. Try it by counting the exponent on x. You've got x to the exponent 0. When this exponent is 1, this is actually your second term. Maybe not everyone had a chance to look at discrete functions in 3U, but this should sound familiar for those of you that have seen this, that you're in a geometric sequence. Your second term has only one multiple of r. Your first term has 0 multiples of r. So this is term 1, that's term 2. That means that this is term n minus 1, and this is term n. There will be n terms here, which means I can rewrite an addition of n of these terms as n factors of x to the exponent n minus 1. So there's the conclusion, and it's a big one. It means that we don't need to use first principles anymore. That if f of x equals x to the exponent n, f prime of x is n times x to the exponent n minus 1. I don't want you to think that you're just sort of magically moving it down, but it's not a proof that you're going to have to reproduce. You also shouldn't confuse it with logarithmic properties, although they are intimately related. And we'll discover that a little bit later. Okay, I hope that you have an understanding of this. We'll review prerequisite material when we need to use logarithmic expressions. But back here, you weren't just magically moving an exponent into a numerator spot either. So have them separated for now as different applications. But we'll discover that they're related to each other by the end of the course.